famous. Okay, so as we take a look at the chart, what I need to tell you is that honestly, these properties are just shortcuts. True story. I could probably have given you this problem as a test walking in the door today, and you probably would have been fine. So let me show you what I'm talking about. Let's say I was like a super mean teacher, super lazy, didn't feel like giving you any sort of direct instruction on the properties of exponents. You would probably be able to figure these properties out on your own. For instance, let's talk about like x squared times x to the third. I forgot I'm recording you guys. I should probably do this on here, right? X squared times x to the third. I said, walking in the door, hey, this is a test. You must figure out the product of these two things. What would be maybe your line of thinking with regard to doing this multiplication problem, Anthony? Okay, because you know that that's a shortcut because somebody taught you that before. But let's say you never learned the shortcut. What are you going to do? Yeah, you would multiply them. What do you mean by multiplying them, Claire? You're right. Ooh, okay, no, not them. See, this is why pronouns can be dangerous in math class. Yeah, like x squared is x times x, and you're multiplying that times x times x times x, right? What do you get? As Anthony said, you could add the exponents together. You get x to the fifth. And it's out of that that we get the product property. It's not like these properties are invented just, I don't know, because they're fun. They're all based in some logic. If we understand that x squared is the product of x and x cubed is x times x times x, when we multiply these things together, it's not like one multiplication is more important than another. We're just multiplying x by itself 5 times. So out of this, we get, the property that Anthony was mentioning. If you have x squared times x to the third, you're actually allowed to add those exponents together to get x to the fifth. So, long story short, and I saw it a couple times as I, was walking around the room and listening a little bit. If you have x to the power of a times x to the power of b, that's just x raised to the a plus b power. And some of you did get that next one right. You had h squared times h to the sixth. So you're allowed to add the 2 plus the 6. And you get h to the 8th. Notice your base doesn't change. Base stays the same. And number 2, you could actually use this property in conjunction with the commutative and associative properties. In other words, you could rearrange your multiplication and then use the properties. For instance, here you could take negative 2 times 7, and then multiply that times a squared a cubed, and then multiply that times b. What you get, negative 14, a to the fifth, b squared. The power rule, also a shortcut. Let's say I was a super mean teacher, and I said, walking in the door today, you have a test. And I need you to figure that out. X squared raised to the third power. You can write it out long ways to try to think about it. If you have x squared cubed, what's another way to write that? Geo. Exactly. And then you could use the property we just talked about, which is, again, just a shortcut. 2 plus 2 plus 2 is 6. Or, watch this, see x squared? You know that's x times x, right? Times x times x times x times x. What do you get? X to the 6th. So again, how could you look at the 2 and the 3 to give us our 6? Well, in actuality, what we did is we multiplied 2 times 3 to get x to the 6th power. So that's kind of cool. So from that type of problem, we get our power rule. Our power rule says that if you have exponents multiplied together, or sorry, if you have like x to the power of a inside a set of parentheses and then that's raised to the power of b, you're actually allowed to multiply the a times the b. We actually have the power rule for two types of problems. You can apply the power rule to a product, and you could apply the power rule to a quotient. However, you are not allowed to apply it if you see a sum or a difference. We have something extra for that. It's called FOIL. Long story short, you're only allowed to distribute the exponent into the set of parentheses if there is no plus sign or minus sign. If there's a plus sign or a minus sign, you're foiling, which is different. You're allowed to distribute the exponent in if it's a product or a quotient, but not a sum or a difference. Everybody okay with that? Yeah. So let's do some examples. Hey, look at that. They stole my example. X squared to the third power, we've already established that's x to the sixth. The big mistake I'll see for number 2, we have negative 2m to the fifth, then squared. The mistake I'll see is that my students will, from time to time, forget to distribute the exponent to the coefficient, too. So you got to remember that. So you have negative 2 squared, m to the 10th, times m to the third. What you get out of that is 4 m to the 13th. Quotient rule is also a shortcut. I had you do x to the third over x squared. Working that out using our quotient rule, you have x times x times x over x times x. Right? They kind of reduce out. X over x is 1, x over x is 1, and you get x to the first on top. So can anybody tell me what we do with the 3 and the 2 to get our 1? Yeah, very good. You subtract. You always do the numerator's exponent minus the denominator. So in number 1 here, we have 27x to the fifth over 42x. Common factor is 3, right? So you get 9 over 14 as far as reducing your fraction is concerned. And then we have x to the fifth over x to the first. 5 minus 1 is 4. So you have 9x to the fourth over 14 for that one there. In the second one there, y squared squared y to the fourth over y to the fourth. They cancel each other out. You get 1. They reduce each other out to get 1. Negative exponent rule. I actually call it the upstairs downstairs rule quite often. Show you what I'm talking about with that. I call it the upstairs downstairs rule because my students will confuse it with a property that they make up, I think, called they do a reciprocal idea. And that'll lead you to some mistakes every now and again. So please understand, hear me now. You have a negative exponent in your problem. Number 1, you cannot leave it there. You will never have a negative exponent in your final answer unless it's a scientific notation problem that's kind of different. We'll talk about that later. So number 1, you will never leave a negative exponent in your answer. And number 2, when you see a negative exponent, it does not mean that you just take the reciprocal of everything that you see there. If it's negative and in the numerator, and by it, we said watch our pronouns. When I say a negative exponent in the numerator, I can make that a positive by moving it to the denominator, or downstairs. So if it's negative in the upstairs, I move it downstairs. You have to put a 1 on top. You can't have a topless fraction. That's not decent. Completely inappropriate. Thank you for laughing. That makes my day. I'm glad. So yeah, if you have x to the negative a, you have to move it downstairs, and then you have a placeholder. For instance on number 1 there, do you see how you have negative 5 times x to the negative second, I think? Holy cow. Yes, the littlest font ever. Negative 5 has an exponent. It does. We don't ever write it, but it's there. Negative 5 is raised to a power. Do you know what it is? I see fingers. Yes, 1. Negative 5 is raised to the first power. That's a positive exponent. So negative 5 is fine where it is. It's in the numerator. However, x to the negative second, that's the bad guy. That's the offender. You can't have a negative exponent in your final answer in a problem of this nature. So x to the negative second has to move to the bottom. X to the negative second, move it downstairs, it becomes x squared. Whew, problem solved. No more negative exponents. So nice. So nice. In number 2, I would reduce the 4/8. Probably you would too, I would think, right? You get 1/2. You have k squared over k to the 5th. So we apply our quotient rule to subtract. 2 minus 5, that's negative 3. Uh-oh. Can't have a negative exponent, right? So the 1 and the 2 stay put. K to the negative third is the offending factor in this case. K to the negative third, because it has a negative exponent and it's upstairs, you have to move it to the bottom. So k to the third actually is now in our denominator. I should go ahead and let you know that you could still go back to that whole idea. See how you have k squared over k to the 5th? You could still go back and kind of have them do battle in your head if that helps you. You have 2 k's on top, 5 k's on the bottom. They duke each other out. You still get 3 k's left on the bottom. That's why k to the third is on the bottom. So if you're doubting where your answer goes as far as like, oh, I got a negative exponent, where do I put it? You know, you could always think back to the original problem and have those variables do battle with each other. Duke it out a little bit. You see k to the third wins, it's on the bottom. And the last rule we have, and then I'm going to cut you loose on some good independent practice problems, we have our zero exponent rule. And our zero exponent rule is real simple. It says anything raised to the power of 0 is 1. And that is a true story. We actually already saw it once today displayed. Do you see it? Do you see it, Alec? Where? Under the quotient rule number 2. Very good. If we would go ahead and just subtract our exponents, 4 minus 4 would give us y to the 0th power, and you get 1. So that's kind of why this is the way it is. Y to the 0th power, or x to the 0th power, just reduced out of, you know, having like bases with the same exponent in a quotient with each other. So you get 1. So number 1 here, we have 7 times x to the 0th power. Please be mindful of the fact that just because there's a 0 exponent doesn't mean your problem's automatically going to be 1. 7 has an exponent. See that right there? That's 7? That 7 has an exponent. I feel like this is deja vu. We don't write it, but it doesn't mean it's not there. What's 7 raised to? 1. Very good. So we have 7 to the first power. That's like its own little thing. 7 to the first power is 7. Times x to the 0th power. That is 1. So 7 times 1 is 7. Every once in a while I get kids who get super excited. They're like, oh, yes, 0 exponent. Just put 1. But you got to watch because sometimes there's other numbers in the problem. So you got to keep that in mind. Number 2, you have w to the 4th squared over w to the 8th. You could multiply those two together, so you get w to the 8th on top. Oh, hey, look at that, w to the 8th on the bottom. If we do 8 minus 8, you get 0. Anything raised to the power of 0 is 1. Questions about our chart? You now have a nice graphic organizer that lists out all your properties. I would use it for the next set of independent practice problems you're going to do. You're going to go ahead and take care of, they're in here somewhere. Independent practice 1 has you doing these properties just with numbers. Independent practice 2 has you doing these properties with variables. Independent practice 3 is a mix of the two. So let's just start with independent practice 1 and see how you do. Okay? Walk around, help you out a little bit. Independent practice 1, Looked pretty good as I walked around. 46,656. B is 16. C is 1 over 2,401. Do you see how I showed at least one step worth of work and then gave my final answer? Again, that's how you're going to do your homework tonight. Copy the problem, at least one step worth of work, and then your final answer. Don't forget to check your answer in the back of the book, because you have some odds tonight. Independent practice 2, your first one there, 1 over y squared. And then part B is 1 over a to the 8th, b to the 4th. Any questions about those there? Again, they look pretty good as I was walking around. You're good? And mixing it up on that last independent practice there. 1 over 512 for number 1. Number 2, x to the 14th over y to the 42nd. Again, it's only the thing that has the negative exponent that has to move. Yeah, what's up? Oh, yep. And number 3, you have negative 8 over a to the 9th. This one is causing more consternation than I had anticipated. You had to cube it. Negative 2 times negative 2 times negative 2. That's a common mistake because we got used to doing the distributive property, right, Danielle? I see what you're talking about. Remember, if you're doubting it, this is like negative 2 to the first power. We're actually taking 1 times 3 to get the 3 there. You know what I mean? And then cubing something is different than multiplying it by 3. Okay, any questions? I think to wrap up today, I'll just have you take a look at your vocabulary for tomorrow, and then we'll do some application problems tomorrow. Tomorrow is where we apply our properties from today. What good is this stuff if we don't apply it to the real world setting, right? So the application of this actually comes into play when we talk about scientific notation. This will be where we stop for today. It's the product of a number A, so weird. A is a letter, people. But we're going to pretend it's a number, A, where A is some number between 1 and 10, not including 10. And 10 raised to a power. And we have 2 examples there. We have a number that is written in scientific notation. 1.2 times 10 to the 4th is written in scientific notation. But 12 times 10 to the 3rd is not. And we'll talk about that more tomorrow. You have bookwork tonight. Have a lovely evening. Yes, sir. It'll be great.